Hello students, week 10 we begin a multi-week unit on fractions and their operations, and in this week specifically we will talk about how to build a productive meaning for fractions as well as the connection between fractions and partitive division of whole numbers. Okay, number 1 here. Suppose 10 cakes are equally shared with 5 people. Then a partitive interpretation of 10 divided by 5 reveals that each person gets 2 cakes. Notice all the numbers here are whole numbers. Now suppose that one cake is equally shared with 5 people. To accomplish this, we are going to have to divide, or I can use the word partition, the cake into 5 identically sized portions. Notice that I don't say 5 identically shaped portions. We'll talk more about that in a moment. All right, continuing with our sentence, how do we describe the amount of cake that each person receives? Now they're going to receive less than an entire cake. That part is obvious. We're going to illustrate this below. Cakes can be round or rectangular. I'm going to draw a rectangular version of a cake here. Doesn't have to be perfect, just some sort of box or something that represents a cake. And we want to split this into equal shares. Now there are lots of ways you could do that. You could do it sort of horizontally, make all these strips. You can maybe do it vertically, break it into pieces that way. You can even do mixtures of the two. You can make some pieces like that and then other pieces look like this. As long as they're identically sized, and here we're focused on area, and they don't have to be identically shaped. But just for clarity or for consistency, let's make them also identically shaped in this case. And to divide this into 5 equal pieces, this is going to be a tricky thing to do. Sometimes people will, I'll make a bunch of vertical lines, and I'll do my best guess to think what this might look like if I broke this into 5 equal portions. I'm having trouble making that one be a straight line. Okay, not cooperating. Straight line, please. There we go. Okay, now they don't look identically shaped, and so what you can do is then, adjust these things, move them around a little bit till they stall, till everything looks about the same size. And this doesn't have to be perfect, but you wouldn't want to draw a picture that looked where they're obviously wonky, like something like this, because then it's clear that not everyone's getting the same amount of cake. And if you're being sloppy in your writing, a person might infer that you're sloppy in your thinking, that you don't realize that the 5 pieces have to be identically shaped or identically sized. Okay, that's good enough. We'll say that's 5 equal portions. And the amount of cake that one person receives is just one of these portions. All right, so just to be, let me color the outside squared a different color. Let's make that blue, and the blue represents one whole cake. And each person gets the shaded red portion. We'll say one person's share, or one person's portion, whichever word you want to use. And we need a way to represent this, and we're going to say that that person is receiving, and then we do what's called a fraction, in this case called the unit fraction. We put a 1 over 5, and then we can write the words of a cake. Or that's usually how we say it, of a cake. Or you can just say 1 over 5 and just put the unit cake next to it. This is a good mathematical way of saying it's 1/5 of the cake. The words of the are implied when you say it, but if you also want to write the words of a cake or of the cake, whichever. Now the way that you actually say this is you say 1/5. So when it's written out, it looks like 1, and you hyphenate it, and you do 1/5 of a cake. So the fraction 1/5, let's talk about that right now in the next paragraph. The symbol 1 over a 5 1 bar 5 like that is called a unit fraction. What makes it a unit fraction is the fact that there's a 1 in the top position. And in the example above, its unit is cake, so 1/5 cake is fine, or you can say 1/5 of a cake. And it refers to each person's share. It's really an amount such that if you were to copy that share 5 times, you would reconstitute the whole cake. So 1/5 of a cake is an amount that when iterated or copied 5 times, it makes the entire cake again. Back to the paragraph here. In general, a unit fraction has the symbolic form 1 over a b with a line between them. We say 1 beef, where b is a natural number and it represents an amount such that b copies, or we can now start using the word iterations. Iterations and copies will be synonymous for us, such that b iterations of that amount will combine to reconstitute some whole amount. So b copies of 1 beef of something will reconstitute the entire something. This whole amount can vary in our thinking, so it is important to always be clear about the referent. And back to reading. For example, 1/5 of a cake is not the same amount of food as 1/5 of a slice. So in this unit, and in math in general, when you're talking about it being applied to things, it's always extremely important to be mindful of and to say in your language the units. If you recall, we had an earlier discussion about if someone says, I owe you 5, that's a meaningless statement until they tell you 5 what? $5, $5,000, 5 puppies. The same thing is true with fractions, especially true with fractions because there can be a lot of confusion when people are not being clear in their thinking or in their speech about the units that the fractions are referring to. 1/5 of a cake is not the same amount as 1/5 of a slice. If we just start, so in this entire week and throughout this unit, I will be doing my best to make sure that we do everything in a situational context where we can attach words to our fractions so that it makes sense what we were referring to, what the whole is. Okay, back to reading, starting right here. In each of the scenarios below, use unit fractions to describe the amount of food per portion. Also draw an illustration of each amount. Okay, so 1 slice of something, it doesn't have to even be a cake, a slice of pizza, whatever. A slice of something is equally shared with 2 people. Now, if you want, you could draw a slice of something like a slice of pizza that's got pepperoni on it, or you can just do a more generic representation. You can do a box that represents a slice of pizza. It's a representation of it. It doesn't have to look like it. And I'm going to make that into a little bit better of a box, and I'll go with black again. Having trouble. Sometimes this program makes the boxes nicely. There we go. Sometimes it doesn't. Okay, a slice. So that represents a slice is equally shared with 2 people. So we just want to do our best to visually cut this in half into 2 equal pieces. And you can do it that way, or you can do it, this way, or you could even do it this way, right? These are 3 ways you can cut a box into 2 equal pieces. Let's go with vertical cuts, though. So something like this. And so once again, we have an amount that we're going to call the whole. So this is this represents the whole slice. And if that's the case, then this portion here would represent what we call 1/2. Now, the symbol we do is a 1 over a 2. This is 1/2 slice. And it would be tempting to, if we were to follow the 1 over 5 means 1/5, 1 over 2 should be 1/2. Something like this, but no one says that. So this, when you say this, you want to say 1/2 of a slice. So 1 over 2 unit fraction is read as 1/2. Now, of course, you all know this, but we're talking about this as if I'm presenting this information in a similar way that you might present it to a child initially. Okay, 1 spoonful of something, it doesn't say what it is, 1 spoonful of ice cream maybe, is equally shared with 3 birds. Okay, so this time birds are going to get a portion. So I'm going to do a rectangle, or I could do a circle just for variety. Let's do a circle representation of a spoonful. Of course, splitting a circle into 3 equal pieces is a little bit more challenging. You want to do a cut there, and then you want to make roughly so you can see 3 equal pieces. If you're not satisfied, you can redraw the edges. You're trying to get 3 equal sized pieces here. Focus on one of them. Now the entire circle, so we'll say, the entire circle stands for a spoonful. 1 spoonful of whatever it was. But the highlighted portion here is 1/3 of a spoonful. And if you're, why don't we say 1/3? This seems putting a th at the end of a number is how we represent unit fractions. But with 3, you don't say 1/3, you say 1/3. I'll just write that part there. 1/3 of a spoonful. It's just the way we say it. Now let's do 1 crumb is equally shared with 4 mice. So 1 crumb of something. And I'm going to go back to a rectangle to represent a crumb. And instead of breaking it in, I'm going to break it in horizontally. That doesn't quite look vertical or like it's half. That's good enough. And then cut that in half horizontally. Now you don't have to do it this way, but there's just an option. And I'm going to move that down, maybe right there. It's good enough. So as long as you see 4 equal portions, so that the entire rectangle, right, let's go just all of it, represents 1 crumb, but one of these portions represents 1/4 of a crumb. So 1/4 crumb. And with fourth, you can actually say this one a few different ways. This one does follow the tradition of just putting a th at the end of it. So 1/4. 1/2 and 1/3 are exceptions, but pretty much every other number just puts a th at the end of it to imply a unit fraction. But with 1/4, there's also another way to say it that's acceptable, that's often said, and that's 1/4. So this one has a few different ways you can say it, 1/4 or 1/4 of a crumb. Now it's also true that these other ones, can't just grab that, there we go. There's a 4th right there, there's a 4th right there, there's a 4th right there. So there's really 4/4 here. If you put all 4/4 back together, you get the 1 whole crumb back. Now let's do a case of cakes is equally shared with 6 classrooms. And I'm going to go with a rectangular representation of the case of cakes. Notice it doesn't say how many cakes are in the case, or that doesn't really matter in our thinking right now. So this whole block right here, we're going to say represents 1 case. And I'm going to break it up vertically into 6 pieces. And I'm going to do that first by cutting in half. So roughly right there, looks good enough. And then each of these, do your best to make them look like, cut them into thirds. And already I can see they don't look exactly equal. If you feel like you're off a lot, then you feel free to adjust where you put your vertical lines so it looks a little bit better. We'll just say that's good enough. You have to imagine that that's going to be 6 equally sized pieces that when put together make the entire case. And then of course we are focused on just one of these pieces. And so this amount right here is 1/6 of a case. 1/6 of a case. Okay, Now, when partitioning, let's move on. When partitioning, each share does not need to be identical in every way. They only need to be identical relative to the type of quantity you are considering. So whether you're considering length, area, weight, volume, there's lots of different ways that you might, different kinds of quantities you might be focusing on measuring. And so when you break up something into equal shares, it just matters what that quantity is that you're focusing on. For example, we're going to illustrate how one brownie might be shared equally with 4 people in such a way that the shares are not identical in every way. So I'm going to do this by drawing a brownie as a rectangle again. And I'm going to cut it in 4 pieces by first cutting it into 2 pieces that are equal. And then 2 of my pieces I'm going to, or one side of this I'm going to cut into 2 pieces that way, and the other side I'm going to cut into 2 pieces this way. So the question on the table is, does each of these, if I cut my brownie up this way, does each person, if you're sharing this with people, does each person get the same amount, even though they're different shapes? And the answer is yes, because this side was a half and this side was a half. So that those were equal sized. And then because I cut them up differently, each half was cut up differently, but they were cut up in such a way that I felt very confident that each portion was another half of a half. So this triangle represents 1/4 of the brownie. This triangle represents 1/4 of the brownie. This is 1/4 of the brownie, and this is 1/4 of the brownie. No person here should complain that they're being cheated. They're all getting the same amount of brownie, even though the shapes don't look alike. That's why when I said that has to be equally sized, not equally shaped portions. All right, number 2. Now suppose 2 brownies are equally shared with 5 people. Before we did cakes, we did 1 cake up here shared with 5 people. Now we're going to do 2 brownies in this case, equally shared with 5 people. How do we describe how much food each person receives? Okay, so I'm going to draw the 2 brownies as rectangles. And I'm going to make sure that these are equal, so I'm just going to draw one and then copy it. There we go. So here's our 2 brownies. And what we're going to do is share these brownies with 5 people. There's several ways you might do this. If you do it brownie by brownie, it's probably the most consistent way, but I'll show you a different way you might be able to do this. So I'm just going to share 1 brownie with 5 people. Let's break this brownie up. When you're doing division into 5, it's good to think of the middle slice first and then divide those portions up. That's usually how I do it. And this doesn't have to look perfect, and you can see I'm not going to bother with making these lines straight or everything looking exactly the same. We'll say that each brownie was cut up equally into 5 portions that are equal size. And I'm going to put numbers inside these pieces to indicate which person gets which. Right? So person 1 gets those pieces. Right? And person 2 will get the next piece. Then person 3 will get the next piece. Person 4 will get the next piece. And then finally, person 5 will get the final piece of each brownie. So each person has received an equal amount. But our focus now is how do we represent how much one person gets. So I'm going to highlight what one person gets. Let's say person 1. It doesn't matter which person we focus on. But let's say person 1, because they all get the same amount. So let's just see. Here's how much brownie of each brownie, what portion of each brownie each person 1 gets. So person 1 gets 1/5 of a brownie from the first brownie, and then plus another 1/5 of a brownie. Now, because we're adding something to itself, we can say that they're getting 2 1/5 brownies. And this is often written instead as putting a 2 over 5. and you put that 2 over 5, the way that is said is saying 2/5. So the top number you say normal, and the bottom number you put the THS at the end of it, essentially. 2/5. And that's how much one person gets. Now, another clever way, once you recognize that each person is going to get 2 1/5 of a brownie, then another way you could have done this. All right, let me copy these brownies over here. Let me delete the numbers, and I'm going to share them slightly different. I'm going to actually remove that bar and that bar, and that bar and that bar. So now person 1 gets all that. Right, you see where I'm going with this? Person 2 gets all of that. Person 3 gets a portion of 2 different kinds of brownies. That was green. They're going to get 1/5 from this brownie and another 1/5 from the second brownie. Person 4 is going to get all of that portion of that brownie, and then person 5 is going to get all of that portion. So in the end, they both, if you divide up the brownies this way, you can clearly see they're all going to wind up with the same amount of brownie. The only difference is that person 1, 2, 4, and 5 is going to get one connected brownie. It won't be in pieces. Only person 3 is going to have 2 different pieces. But in the end, they all have the same amount of brownie. So this is a perfectly reasonable way to do this, but we're going to be focused more on this way of thinking, where you separate the brownies one at a time between the 5 people, and then combine the parts for each person. Now the symbol 2 over 5 is called a common fraction, and in the example above, its unit is brownie, and it refers to each person's share. So when I say 2/5 brownie, we're talking about the fact that 2 brownies were shared with 5 people, so 2 over 5, or 2/5 brownie, is how much each person gets. In general, a common fraction has the symbolic form a over b. So I'm reading this sentence now. So we have this a over b, where a and b are natural numbers. Now remember, the natural numbers are 1, 2, 3, etc., the counting numbers. They don't include 0. So we're not letting a or b be 0 right now. We're just talking about fractions where a and b are not 0. They're only 1, 2, 3, 4, etc. That's called a common fraction. And it represents, so when you see a over b, or a bths, is the best way to say that instead of saying a over b. I like to say a bths. So a bths represents a iterations of an amount such that b iterations of that amount would form some whole. So another way to say this, say it in a mathematical way, is written right here. So if we say a bth things, so maybe a bth of a brownie is equal to a iterations of 1 bth of that thing. So in the case of our brownie example, we would say 2/5 of a brownie means literally 2 iterations or 2 copies of 1/5 of a brownie. This is similar to simply saying that a over b can be thought of as doing a times 1 over b. Or a bths is the same thing as doing a times 1 bth. And I just like to put the units here, even though I'm being general here, because you should always be thinking about something. It's a bths of something and 1 bth of something. And that something can vary from person to person. And that's why it's important that when person A is talking, that they are clear about what the fraction is referring to, so that when person B hears the fraction, they are able to visualize the same thing. It's like, once again, like 1/5 of a cake is not the same thing as 1/5 of a slice of a cake. Now suppose 7 gallons of water are equally shared with 5 people. All right, so you can imagine what I'm going to do here. I'm going to use these boxes again to represent gallons of water this time, but we have 7 of them. So there's only, those 2 boxes represent 2 of my gallons, and I just got to copy this and paste it a bunch of times so that to the point where we have 7 of them. It doesn't really matter that they're all in a row. Let's just copy one more. So these boxes represent the 7 gallons of water that we're going to share with 5 people. Describe how much water each person gets, and illustrate the situation below. So I'm beginning my illustration. Each person is going to get 7 copies of 1/5 of a gallon. I think I can do something like this now. Copy. So I'm going to extract these shaded portions, put them all side by side. And we need 7 of them. Okay, so there's our 7. I'm curious if I don't want to do that. These 1s that are written there simply refer to that's person 1, right? That doesn't mean that it's 1 itself. The numbers were just to indicate which person got which. So I put those numbers in there to indicate people, who's getting what, but they're not there to indicate that that there's 2 in that box or something like that. It's just that person 2 gets that sliver. So let's just be clear about that. If I were to take these and put them next to, you can see that each person is going to wind up getting more than 1 brownie total. And since each of these slices represents 1/5 of a brownie, oh gosh, I really wish I could erase those 1s. I just don't like them in there. Those 1s make me think that each value is 1, and so I'm thinking I'm seeing 7 here, but each of those is 1/5 of a brownie. I'm going to take a moment and do this. Ooh, no, I could have done this. I have an idea. Just grab the shading. Yes, aha, look at that, so clever. They don't want those there. Get rid of that. I just wanted the shadings. In reality, it's probably best to put the fractions 1/5 in each of these. So each of these represents 1/5 of a brownie. And this is what person 1 gets. The person 1 share gets this much brownie, and we say that this represents a total. You can say it's 7 copies of 1/5 of a brownie, or you can just say it's 7/5 of a brownie. And some of you will notice that if you take 5/5 and put them together, that makes 1 brownie, 1 whole brownie. So I'll introduce this notion of mixed numbers right now. So you could also write this as a person gets 1 whole brownie plus an extra 2/5. And with mixed, this is called a mixed number. It's a part whole number and a part fraction. And sometimes those mixed numbers are put, the fraction is written smaller right beside. I don't know if I really like doing this because usually when you put something side by side and you don't put a symbol in between, we saw this back when we talked about multiplication, that the default understanding is that you should multiply the 2 things. But really what's happening here is that we're adding 1 and 2/5. So when you see this, you should say 1 and 2/5 brownie. Or you can simply say 7/5 brownie. Okay, that's enough for that example. Let's go on to number 3. Let's just talk about what fractions are in general. A general fraction is any expression of the form capital A over capital B, where capital A is called the numerator, capital B is called the denominator. And capital A and capital B can be anything. They don't have to be whole numbers, they don't have to be even numbers. And we can still call the thing a fraction. In this unit, we will simply use the term fraction to refer to a common fraction, as defined earlier. So back up to what common fraction was. A common fraction, it was this sentence right here. A common fraction is A over B, or A bths, where A and B are natural numbers. And so I don't have to keep saying common fraction, common fraction. When I just say fraction in this unit, I'm referring to this, a common fraction. It has to be a fraction where the numerator and denominator are counting numbers, are natural numbers. A proper fraction is a fraction. Reading right here next. A proper fraction is a fraction. Notice I just said fraction without anything, so that means a common fraction. So I could read this as a proper fraction is a common fraction where the numerator is less than the denominator. And an improper fraction is a fraction, or a common fraction, where the numerator is greater than or equal to the denominator. We're going to make a little Venn diagram here to demonstrate the relationship between general, common, proper, improper, and unit fractions. Okay, so the most general thing are the general fractions. So let's do a big block for that and call this the, and I'm going to leave the word fraction off. We're just going to say the word general in here. And just to make sure I have enough space, let me make that even a little bit bigger. Okay. Anyway, so there's our circle that represents general fractions. Now, as a subset of that, we have common fractions, or things I'm just saying are fractions. But I'm just going to write the word common. Oops. Let's make that nice and big too. Common fractions are fractions of where the numerator and denominator are natural numbers, and that could be split into two different kinds. So I'm going to split this down the middle, where on one side we have the proper, and on the other side we have the improper. And then unit fractions. Unit fractions are of the form 1 over a number. And in order to be a fraction, let's go back to where a unit fraction was. I should have said this up here. I said, in general, a unit fraction has the symbolic form 1 over b, where b is a natural number. I should have also said that we want b to be at least 2 or higher. Because if you have 1 over 1, then you could write, that would technically be a improper fraction that's also a unit fraction. It's sort of this anomaly, but it's not an interesting example, so I just want to be careful to discuss that case. Back in our Venn diagram, we're going to consider unit fractions to have denominators that are 2 or higher, which means the numerator is 1 and the denominator is 2 or higher in order to be a unit fraction. That puts unit fractions in the proper. Now, if you want to say that a denominator of a unit fraction could also be 1, then technically unit fractions would be in both portions here. Let me do it this way. All right, let's start doing some examples. Let's start with the unit fraction. An example of a unit fraction, I'll do a different color here. So 1/2 is a unit fraction. It's also a proper fraction. It's also a common fraction. It's also a general fraction, because this 1/2 is inside all of those circles. However, it's not over here, right? It's not inside the improper. So the only thing it's not is improper. 1/3, 1/4, all of these unit fractions, etc., forever. The only unit fraction you might argue is improper is if you say 1/1, which is not a very interesting one, but technically when you have the numerator is the same size as the denominator, then we have the improper situation. Okay, so now I want to put an example of something that's not unit but proper. So this would be something like 2/3. Any fraction of two counting numbers you can make where the top is smaller than the bottom, where the numerator is smaller than the denominator, would be an example of something that would be proper, also common, but not unit. So, I don't know, 4/7 would be another one, etc. You could just infinitely many that you can come up with. Improper ones would be where the numerator matches the denominator, or the numerator is higher than the denominator, so, etc. Now you might realize that sometimes you recognize that 3/3 is the same thing as 1, and as soon as you write it as 1, it's technically no longer a fraction. So if you did simplify it, an example of something that's not even a fraction at all would be like 1 or 5. You can even argue that decimals aren't fractions. So we'll talk about decimals later in the semester, but 1.2 is not a fraction because it's not written as a fraction yet, although it could be expressed as a fraction. We'll talk about that later. Now, a general fraction that's not a common fraction would be when, say, maybe you have expressions involved, like x/3. We're going to call that a general fraction, but the top is not a counting number, but the bottom is. Or other examples, sometimes you get really complicated expressions. You might have seen like x plus y over z. Or if I do a decimal involved, 1.2 over 5. Or a negative involved, like a -2 over a 7. Right? Because we said that to be a common fraction, that we want the numerator and denominator to be natural numbers. But in this case here, this is not a natural number involved. So it's still going to be a general fraction, but we're not going to consider it a common fraction. Okay, I think we've put examples in all the different positions to help you understand what these different terms mean. And the reason 1.2 is because, this can be converted into a common fraction, but it's not currently written as a common fraction because 1.2 is not a natural number. But decimals we haven't talked about officially in this class. That's to come a little bit later. Fractions can be modeled using manipulatives such as fraction circles or fraction squares. Represent the following fractions using both fraction circles and fraction squares. Imagine a context and simplify what each referent whole is. Oh, and specify, not simplify. Specify what each referent whole is. Okay, so manipulatives that are fraction circles or fraction squares, I'm going to show you some virtual manipulatives, and the website that I'm here, it's pcmathoer.wordpress.com. A link to it is in your Canvas, so you can find this link. It's on the week 10 page. If you click on virtual manipulatives tab right there, it brings up a whole list of different manipulatives that others have discovered. Look at the one here in the top right, the integer chips. That's one that we've already used once, and this is where I got it. But this has a whole bunch of others that you're encouraged to explore. Not for this unit, but for this unit, I want to look specifically at what's in the top right currently, which is fraction bars, and what's in the bottom middle currently. It's called fraction circles. Let's tap on fraction circles. And then this takes you here, and then tap on this image over here on the right to open the tool. Okay, the drop zones just tells you how many different circles you can be working with, 1, 2, 3, or 4. Right? You can say, hey, if I click on this one and tap this, it drops that pie wedge over there. If I want to remove it, just drag it to this trash can symbol. So you can, how many drop zones do you want? Do you want just one? So just click on, there we go. I guess I had to click on that top left and then click on that one. And we have just one drop zone. And if I drop the entire circle, that stands for a whole of something. Let's get rid of that. Tap the pink, it puts that in place. Tap a second pink, and notice what it does. It shows us that two halves combine together to make a whole. Let's get rid of those. This orange one is a third, because if you tap it 3 times, you can see that it takes 3 of them to reconstitute the whole. Start over, etc. Orange is a fourth or a quarter, and it takes 4 quarters or 4 fourths to reconstitute a whole. The green is a fifth, I believe, because it's going to take 5 of these green wedges to reconstitute the whole. Start over. Turquoise is a sixth. Notice 3/6 made the same amount. That's equivalent to a half. Something to think about, but 6/6. There we go. And if they're not going in the spot you want them to go, just kind of move them around and see if it smartly picks up where it should go. There we go. That looked nice. And so 6 of those, 6/6 makes a whole. Also, if you throw a piece in there, you can rotate it. Notice the gray little dot. If you grab that dot, you can rotate and put that piece kind of wherever you want in your fraction circle. The blue, let's see what the blue is here. 3, 4, 5, 6, 7, and 8. So it took 8 of them. So the blue is 1/8. We don't have a 1/7 here in this particular tool. Let's see what the purples are. Looks like 5 of them made half the circle, so I'm guessing 10 of them will make the entire circle. So each purple wedge is 1/10. And then finally this gray one. Let's see what happens when I start throwing these grays in there. To get to half the circle took 6, so just 12 is going to make the entire circle. And so we have 1/12 is the gray. Down here in the bottom left, you can add transparent pieces. So if you, let's say you put a half in there and you say add some transparent pieces, and we're curious how many quarters it takes to make a half. So I can put a quarter in there, make it transparent, and then grab that, just grab the gray only and rotate it, so, and put a second quarter in there. And you can see right there, 2 quarters perfectly overlapped 1/2. This is the fraction circle manipulative tool. Since we don't have manipulatives to work with, since we're working online, you can use this to play with your fractions. There's also one that's fraction bars or fraction rectangles. You can just drag these things down, kind of put them in place, snap to grid. I don't seem to be able to change these settings down here on this iPad, so it's not sure why, but okay, well, I'm not sure why this doesn't seem to be working on the iPad. It'll work better if you go straight to the web page and do this with your mouse. Well, let's start over. So the gray represents a whole, and the green clearly represents a half. And once the green is down, you can tap these boxes to shade different amounts. So there's a half, there's a second half. You can see it's the same length as a whole. Oops. And then you can drag that away to the trash can. You know, if you put this yellow in there, or drag this down, you can see that each of these yellow boxes represents a third, because 3 of them make the whole, etc. So these are going to be good tools to work with students, or things like this anyway, so that they can recognize facts like the following. If I were to, the green stands for a half, and if I wanted to say, and the red stands for a sixth, if I want to say, well, how many sixths does it take to make a half? Well, you just have to say, oops, there we go, 3/6 winds up being the same amount as just 1/2. And we start to introduce this notion of equivalent fractions, which we'll talk more formally about in just a moment. I just wanted to show you these virtual manipulatives that can be used to help build an understanding about fractions and equivalent fractions. Let's go back to our notes. I'm just going to do this by hand. I'm going to draw pictures by hand. Represent the following fractions using both fraction circles and fraction squares. So 3/4. Let's draw a whole circle and say this represents a whole. And it says invent a context. So what do you want this to be? A whole what? A whole pizza? So we're going to say we want to do 3/4 of a pizza. And I picked pizza simply because pizza's are round. And so the circle also represents a visual of what the pizza might look like. And if we want to do 3/4, you have to break the pizza into halves. So I'll do this horizontally and then vertically. So this broke the pizza up into fourths. So right here, this would be 1/4 of a pizza. But now we want to do 3/4 of a pizza. So then do a second fourth. Oops. And then well, I'll do this. 3/4 of the pizza. It's all this. All right, you get the idea? So here's our representation of 3/4 of a pizza. Even though we're talking about a pizza, you could still represent this visually with a rectangle and say, okay, well, here's my pizza, and I'm going to break it into fourths this way. You can go horizontal the next one, doesn't matter, or you can go more of these. Well, let's just pretend those are all even, or equally sized, I should say, and then shade in 3 copies or 3 iterations of 1/4. So both of these are representations of 3/4 of a pizza. Now let's end the whole. It's always important to specify what the whole is. So well, let's just do it this way. I'll just write this way. Entire circle. This is one of the nice things about doing circles, is that when a circle is complete, it's obvious. But when you're working with rectangles, it's not always clear that you've finished your rectangle, right? I could put more pieces on here, and how do you know when it's technically finished? But when you're working with a circle, it's easy to see that the circle has been completed. So in the case of using rectangles, you could do something like this and say that this stands for a whole pizza. Rectangles are going to be nicer tools in general, I believe, to work with. They allow you to divide them, partition them, crisscross patterns. The circles are difficult for doing that, but the only advantage a circle has is that it's obvious what you're thinking of as the whole, and that's typically an entire circle. Let's do this 10/3. It's invented context. Let's do 10/3 of an hour or something like that. Just get some time involved. And if I was using fraction circles, here we go. There's one circle. Well, let me first, before I copy these, let me take this one circle and break it into thirds. And this is tricky to do with circles. You kind of want to make this like perfect Y in the middle. And it represents breaking that circle into thirds. That's good enough. We'll pretend that those are equal pieces. But this only represents, currently, if I were to start shading, there's only 3/3 right here. So I need another whole circle to get up to 10/3. So I got to do another one. So I'm going to copy and paste. Okay, so there's another 3/3. So I have 6/3 so far. I need 3 more at least. There's 9/3. I got to do another, but not shade all of it. Just pick one of these to shade, and there's a total of 10/3. Now each circle itself is 1 hour. Represents 1 hour. And what's shaded represents 10/3 hours. Or you can also see that it's going to be 3 1/3 hour, right? This is, we'll talk more formally about mixed numbers here in just a moment, but 3 1/3 hours is the same thing as 10/3 hours. And if you were to do this using rectangles, I don't need to spend too much time doing this, I don't think, but there's 1 hour, and I broke it into thirds, and so I'm going to shade. There's 3/3 shaded right now, but I need to get up to 10/3, so I'm going to have to do some copy and pasting. And the thing with rectangles is sometimes you want to put them side by side, like touching, and so it can be confusing about what's what. If you keep them separate, it's easier to keep the holes like separate to see the different hours. But sometimes people draw them next to each other, and this can add a little extra layer of confusion, but I'm going to go ahead and do that anyway, just to make sure that we label this picture nicely. I don't need all 3 of those pieces here, just needed 1 of them. And I'm going to label my pieces this way, and I recommend you do something similar. So 3 of these was 1 hour. That's the whole. One of those, right, one portion of that is 1/3 of an hour. Or you can say 20 minutes. And so from here to here, therefore, represents 10 iterations of that. And so we have 10 1/3 or 10/3 hour. All right, so this idea of identifying what the whole is. Now this is especially important right here. When I drew all of this just sort of lumped together like that, without this label right here telling me what the whole hour was, it's impossible to know, right? I might have, like, where's the whole unit here? Maybe this was a whole hour and I broke it up into sixths, right? So you definitely need a label like this to help establish what 1 is. So then you can then establish what 1/3 is, and then what 10/3 is. And this idea of establishing what the whole is is called unitizing. It's establishing your unit. It's saying 3 of these pieces put together make 1 unit. So each piece itself is 1/3 of a unit. And 10 such pieces is 10/3 of a unit. And that is what is being described here with this last sentence. The act of identifying a referent whole is called unitizing. Okay, number 5. It is possible for one amount to be represented by 2 different fractions, depending on the referent whole. This requires unitizing twice and maintaining those 2 levels of units simultaneously. Now, when I say 2 different representations, 2 different fractions, I'm not referring to equivalent fractions, which you might be thinking this means. Like 1/2 and 2/4 are considered the same value. We'll talk about that in a moment. That's not what I'm referring to here. I'm going to make a claim that something like this could be true, which you might, at first your glance is, your instinct should be that no, that's not true, and it's correct. This is not true if the units are the same, but it is true potentially depending on what units you put on there, but they would have to be different units. Let's consider this example that's described right here. Suppose, as reading right here, suppose 3/4 of an orange is 1 serving. Find 2 ways to describe the size of the shaded portion below. Okay, so here's our drawing of an orange. The shaded portion is this portion right here that we're talking about. And we know that, I think it's pretty clear looking at this picture, that if I were to cut this orange in half and then in half vertically, that it looks like what's shaded is one of those 4 pieces. So I feel pretty safe that describing what I'm seeing there as 1/4 of an orange, but make sure you put the unit. 1/4 of an orange is shaded. However, 3/4 of an orange makes a serving, maybe a serving of vitamin C or something. So if I were to highlight 3/4 of that, it'll look something like this, right? This is a serving. And let's make it let's just point at this. This is 1 serving. If that's 1 serving, and then I break that here, and then I shade this portion, then how much is shaded? Right? This is where circles become problematic, because we're so used to seeing a circle we're so used to seeing something that looks like this, and then instantly saying that that represents 1/4. Well, it's true that that represents 1/4 of the entire circle, but it doesn't represent 1/4 of a serving, because a serving isn't an entire circle. A serving is just 3 portions. And 1 portion shaded means I've shaded 1/3 of a serving. So this shaded portion right here is just 1/3 of a serving, because 3 of them make up an entire serving. Right, so this is what I mean when I say that it is possible for one amount, and that amount is the same amount of orange, but it can be represented by 2 different fractions depending on the referent. And we're unitized twice. When I'm thinking servings, I have a different visual for what an entire serving is. When I'm thinking oranges, it's the entire circle, is the entire orange. All right, so we can produce a statement that looks a little bit like the following. Let's move that down here, 1/4 of an orange. Oops, I don't want that. So I'm effectively able, because of this problem here, to make a claim like this: 1/4 equals 1/3. And if you only write that without a context, people will push back and say this is a false statement. Well, that's technically true. This is false, but under the assumption that the 1/4 and the 1/3 have the same unit. It can be a true statement to say, but you want to make it clear what the units are so that this is true, right? So you would say 1/4 orange equals 1/3 serving. So it's super important that you have units next to your fractions as we continue to move forward, because there's going to be a lot of multiple levels of units that you have to maintain as we talk about fractions of fractions, and etc. It's going to get even more complicated than this. Draw a representation of 11/4 apples. Okay, so let's go with, since apples are round, let's go ahead and just do the round apples in 11/4. So here's one apple to represent. I'm going to break it into fourths and shade in. There's 4/4 shaded, and we want 11/4 total, so I'm going to have to copy and paste this. Right, there's a 8/4, and there's 12/4. I already have too many. I only needed, so I'm going to delete that shading and shade 3 more of these fourths of an apple. And you can see now I've shaded a total of 11/4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11/4 are shaded. Express this value as a whole number combined with a proper fraction. This is called a mixed number. So here's our formal discussion on mixed numbers. We have a whole apple. We have 1 apple plus 1 apple plus 3/4 of an apple. And I'll just put the unit here after all of them. And so we can make the following claim, that 11/4 of an apple, or 11/4 apples, because I usually will put a plural, make this plural, if I recognize that I have more than one shaded. And since we have more than one apple shaded, I'll make the word plural. But if this had been 1/4 of an apple, I would probably just take that S off. That's why I didn't put an S when I said 3/4, because it was less than 1. It's just it's a nuance. If it's 1 or less, we tend to make the referent singular, and if it's more than 1, we tend to make the referent plural. But I guess maybe that's up for debate. So we have 11/4 apples. It's the same as saying we have 2 3/4 apples. Okay. So we can make a mixed number out of this. Mixed number is part whole, part proper fraction. Notice that, so the part that's whole is the 2, and the part that's a proper fraction is the 3/4. And proper means the numerator is smaller than the denominator. Because technically you could also say the following. You could say that instead of saying it's 1 plus 1 plus 3/4, we could have said it's 1 plus, and then the rest of it was 7/4. So I could make another mixed number, say it's 1 7/4 apples. But this is generally not the acceptable way of describing, of writing a mixed number, because the fraction that's involved is still improper. It's not proper yet. So if we make sure that that fraction is a proper fraction, and then we have what's considered to be a mixed number. So let's not go that route. Okay, I think we've done everything we need to do for that part. Now, it is important to realize that a mixed number represents the sum of the whole and the partially whole components. Right, so if I go back up to here, that when you write the 3/4 next to that 2, it's the implied operation is that they're being combined, in other words, added. It's the sum. It's 2 3/4 apples. Okay, now let's also just do an example where we go from mixed number to an improper fraction. Suppose a trip takes 3 2/5 days. Express this number of days as an improper fraction. So I'm going to use rectangles this time to represent a day. So there's 1 day. And we have, I'm going to copy and paste it, and I'll make them adjoined. Although some people will say, don't do that, make them separate so you can see what each hole is better, especially when I start making other vertical bars through here. But I'm going to go ahead and put them together and just show you how I'm going to repeat how I keep them distinct. Okay, so here's 1 day, a second day, a third day. So there's 3 whole days, and this last one you just need to do a 2/5 of that. So I need to break this last one into 5 equal pieces, 5 equally sized pieces. This will be good enough to pretend. And then I'm going to shade in. Oops, went too far. Let me make this marker a little bit bigger this time. There we go. There's 3 2/5 shaded in. Okay, so this represents 3 2/5 days. Express this number of days as an improper fraction. So I'm going to break up all of these into fifths. And this is where it can be confusing because the boxes, I made them be adjoined to each other. But if I do, something similar and break all of these up into fifths, and this won't look perfect, but there's the first one broken up into fifths. And you can see that because I made them adjoined, it's easy to lose focus of where each day started and stopped. You see this problem that's occurring? There are a couple ways around this. Make a longer line separating the days. Something like this to keep the days separate. That's one way to do it. And then we can also do things like this where we say, okay, well, 5 of them is 1 day. One of these little pieces is 1/5 of a day. And here we see, well, how many do I have shaded? Well, each day is 5, so we can say, well, there's 5/5. Here's another 5/5. Here's another 5/5. And then we have 2 more fifths at the end. So how many fifths total do we have? We have a total of 17/5. So this is how you would convert a mixed number, 3 2/5 days. Just break everything into fifths and count how many fifths total you have. And we have 17/5 total. Okay, let's go to next question, number 7. For each image below, one circle represents a whole. Okay, so that's important to specify because this is like the serving. It's possible to look at this Pac-Man green shape and think of that as the whole, but the whole is actually the entire circle. Okay. One circle represents a whole. Represent each shaded amount as a fraction with the indicated denominator. Okay, so how many fourths is this green thing? If I were to use the manipulative tools over here, the fraction circles, well, there's a fourth, and if I just figure out how many fourths it takes to make something that looks like the green thing, or is at least the same amount of space, and don't forget you can move these things around. There we go. So now it looks, what's shaded here in yellow looks exactly like what's shaded here in green. And I can do finish up the partitioning of this. So we see that there's 1/4 of a circle there, 1/4 of a circle there, 1/4 of a circle there. And so we have a total of 3/4. Okay. Now let's do this with eighths. Okay, the eighths, if you recall, was the blue one. So I'm going to start throwing some eighths on here until we've covered the same amount of space as the yellow. So there's 1, 2, 3, 4, 5. Let's put that over on this side, and 6. So it looks like 6/8 covers the same amount of space as 3/4. Now, it's probably a good idea to draw this in your notes a few times, but I have the luxury of here being able to erase this work and putting in new lines. So now I want to represent how many eighths. All right, so that was 1/8. That was 1/8. Here's an eighth. There's another eighth, and then we need 2 more eighths. So in the end, we get a total of 6/8. We'll represent that same amount. And then the last one's how many twelfths. I think we had twelfths in here. It was the gray one. So let me move all these eighths out of there, but I'm going to keep the 3/4 because we want to cover the yellow again. But I want to do this with the twelfths. So 1, 2, 3 twelfths covers one of the fourths. So another 3 should cover the next fourth. And then this will have to be rotated over here. And then the last 3 will cover the last fourth. Okay, so each fourth has 3 twelfths in it. So we need a total of 9/12 to cover. And I'm not going to redraw that here for time's sake, but we can see that 9/12 is what's needed. Now, all of these fractions look different. I think you'll agree. But they all represent the same amount of a circle. Okay. We'll make comments on that in just a second. Let's do the same thing with the reds here. Thirds. Okay, so I want to have 2 drop zones. Let's delete everything first. Start all over. 2 drop zones. Let's first drop into the, this is where I can choose where I'm dropping. So let's drop into here. I'm going to tap the thirds. 1, 2, 3 thirds. And then remember, trying to match, oops, this shape here. Looks like another 2 thirds might do it. Let's see, 2 thirds. Oops, I've dropped to the wrong spot. Let's get rid of that one. Let's drop to this circle now. There's a third and another third. And I just need to rotate these so that they are look more like, let's rotate just like there. This is tricky to do. Trying to make it look exactly like our other picture. I'm just good enough. Okay, so I've oriented them so that it looks exactly like this picture. So I think it's pretty safe to just assume that that's a 2 thirds over here. And if you split this one perfectly down the middle, and then all right, so we definitely see there's a third, a third, a third, a third, and a third. So that's a total of 5 thirds. Now let's do this in sixths. All right, let's drop back to this circle and throw the 6th in there. The 6th were the turquoise. So there's 1/6, 2/6. So right away you can see that 2/6 covers a third. All right, so if I keep going, you can see you need a total of 6/6 to do that full circle. Oops. Drop over here now. 2 more 6ths. And I need this to be over here. And then 2 more 6 to finish us out. So if we do this in terms of sixths, I have a total of 10 sixths. And then 12ths. Okay, so let's get rid of all the sixths. Get rid of all that. Take all those out of there. Man, let's do 12ths. Just drop back here and start throwing in those 12ths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 12 twelfths make the whole circle. Oops, drop to the wrong one. Now let's drop over here. Let's see where that goes automatically right there. Okay, so 1, 2, 3, 4 more 12ths make up one of those thirds. Pretty much 4 twelfths will make up 1/3. And since I have 2 thirds in that second circle, I need 8 twelfths. So let's get these other ones into play. And you can see we have 12 twelfths plus 8 twelfths. That's 20 twelfths total. So 20 twelfths is another way to represent that same amount that's shaded. Okay, so just like in the greens with these reds, all of these fractions, they all look different. So on the surface, they appear to be different, but they all, in the end, represent the same value. Of course, assuming that we're referring to the same referent whole. 5 thirds of a full circle is the same thing as 10 sixths of a full circle. Same thing as 12 or 20 twelfths of a full circle. Looking over here, 3/4 of a full circle is the same thing as 6/8 of a full circle, which is the same thing as 9 twelfths of a full circle. This introduces this idea of equivalent fractions. So reading down here, 2 distinct fractions, and I say distinct meaning that they look different, right? So 6/8 does not look the same thing as 9/12. So we're going to call those distinct. 2 distinct fractions are considered equivalent if they represent the same amount of a quantity, if they have the same value. So they look different, but they have the same value. It's kind of like saying that 4 plus 4 looks different than 8, but they have the same value, right? You combine, these are the same value, even though they look different. That happens with fractions. 6/8 and 3/4 look different, but they have the same value. They represent the same amount when referring to the same referent whole. Back to reading here. In general, we can make the following mathematical statement where a, b, and c are any natural number, and assuming the fractions have the same referent. Right, if they don't have the same referent, then crazy things can happen, like up here, right? A fourth and a third can be the same if they're not referring to the same thing. So only when they have the same referent do we talk about fractions being equivalent. And you'll notice the patterns were, right, if to go from 5/3 to 10/6, if you double the number of pieces you're dividing the shape into, then to preserve the same amount, you have to also double the number of pieces that are the number of iterations. Right? So if I break a circle into 3 pieces and then do 5 iterations of that, and if I break up the circle into 6 pieces, I'm going to need twice 5. I'm going to need 10 iterations of the 6 pieces to wind up getting the same amount as doing 5 iterations of the 1/3 of the 3 pieces, where each piece is a 1/3. So you get this idea that you can create equivalent fractions by simply multiplying the top and bottom by any number you want. So if I double the top and bottom, you get 10/6. And if I double those, I get 20/12. Or you can, to go the other way, you can use division, right? You can divide 10 and 6 by 2 each, or multiply them each, or divide them each by 2, and you get 5/3. So you can go forwards and backwards. You can make more complicated looking expressions or less complicated looking expressions that are considered to be equivalent. And that's what this is saying to do. It's saying if you want to go this direction, then you multiply top and bottom by c. If you want to go this direction, then you divide top and bottom each by c. And you can make equivalent fractions. So if you have 30/18, without drawing pictures, find 4 new fractions that are equivalent to the fraction below, one of which should involve the smallest possible numerator and denominator, which we say is in simplest terms. All right, so I'm going to start breaking this down. The formal process looks something like this. You do factoring. So I can recognize that 30 is 15 times 2, and that's the same thing as, and put that over, and then factor 18 into 9 times 2, and then you can effectively ignore those 2's. And say this is going to be the same thing, therefore, as 15/9. Right. That's like me going here and ignoring the c's, changing it to just a over b. And I don't say ignore. In reality, you have a 2 divided by 2, which is a 1, and 1 times 15/9 is 15/9. But when you're thinking in terms of fractions and pieces, it's almost as if you ignore the 2's. They're not there. And then I can continue this. I can say, well, 15/9, 15 factors into 5 times 3, 9 factors into 3 times 3, and now I can ignore these 3's. I can cancel those 3's, and I can say that this is equivalent to just 5/3. Once you get to the point where your numerator and your denominator are relatively prime, then you can't go any further. Because even if you could factor, now they're both prime themselves, but even if I had something like 10/3, right? 10 is 5 times 2, and 3 is prime. They have no common prime factors, so 10 and 3 are relatively prime, and you would say that this is in simplest terms. So you just keep this up until you get down to a numerator and a denominator that are relatively prime, or prime themselves, and we have our simplest terms. Now we're supposed to find 4 new fractions. So let me circle the ones. Here's one new fraction. Here's a second new fraction. This is the one that's we're saying is simplest terms. But we're supposed to do 4 more. So if I take the simplest terms and double the top and bottom, I create a new fraction. So I could say that 10/6. Right? I could say, hey, double the top and double the bottom. And we have 10/6. There's another fraction that's equivalent to 30/18. Notice I could have got from 30/18 straight there by dividing top and bottom by 3. That would have taken me straight there. Now I could double again, or just for argument, I could triple. If I triple, I'm going to get this one again, and I need 4 new fractions. That's not a new fraction. I could double and get a new fraction. That would work. Or I could, just for the sake of argument, multiply top and bottom by 5, just to pick a number. So I could say 10 times 5 over 6 times 5, and say that we get 50/30ths. So here's another fraction that's the same value as 5/3, provided all these fractions are referring to the same referent whole. All right, number 8. Suppose you have a green and a red strip of paper, as indicated here. If the green strip is 1 unit long, then how long is the red strip? Express your answer in 2 ways. Okay, so our first assumption is that this is 1 unit. So you can clearly see that the red is 1 unit plus another 1 unit, and then we have to figure out how much this is. Well, if you imagine those two, notice the 1 unit is composed of 4 pieces, and this is 2 of those 4 pieces. Or you can think of the 1 unit as really being 2 pieces, right? See those 2 pieces? And then this red unit is just 1 of those pieces. So you can say that that red is either 2/4, or you can say it's 1/2, right? You get this idea of equivalent fractions. It doesn't really matter. If I want to go with simplest terms, then I'm going to go with the 1/2. So there's a half of a unit there. All right, so I could say, therefore, that the red strip is 2.5 units. How long is the red strip? Okay, 2.5 units, if the green is 1 unit long. Express your answer in 2 ways. So there's a mixed number way. Right? Another way we could do this, let me erase all that. We could say that, well, the thing I shouldn't erase is the fact that this represents 1 unit. So I could go and say that each of these represents a half, and then just count how many of those there are. Right? Don't need that last one. And you say, okay, I see 5 halves of a unit, so you could say 5 halves units. Or you can even do this. I mean, here's a third way. I said just do it 2, but here's a third. Right? Each of these actual little squares here is 1/4 of a unit. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those. So I could also say, therefore, that this is 10/4 of a unit, or 10/4 units. There's a variety of ways of doing this, but everything was assuming that the green was 1 unit long. Okay, now we're going to switch our assumption. If the red strip is 1 unit long, then how long is the green strip? Okay, so now we have to say that the red strip is the 1 unit. So we've just re-unitized. By identifying what a unit is, that's called unitizing, and now we just re-unitize because we just did it a second time. And if the red strip is 1 unit long, then how much of the red is one of these little boxes? Well, how many were in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each of those is 1/10. Because 10 of them make the entire red. Therefore, you're going to have a 1/10, a second 1/10, a third 1/10, and a fourth 1/10 will be how long the green is. So the green will be 4/10. This says express your answer in 2 ways. Well, could I do a mixed number for this? Well, no, I couldn't, because if the red is 1 unit long and the green is shorter, then the green can't be written as some whole amount plus some non-whole amount. So there's not a way to write the green length as a mixed number because it's less than 1. It's less than 1 unit long. So we need a second way, though, to write 4/10, and I think you're probably seeing it. It's going to be 2/5, right? Look at the collection of 2 boxes. Right, there's 1, 2, 3, 4, 5. So each of those is 1/5. Each collection of 2 boxes is 1/5 of the unit. And then up here, we therefore see that the green is 2 of those, right? 1/5 and another 1/5. So you could also say that the green, therefore, is 2/5 units. And now that I'm realizing that 2/5 is less than 1, I'm going to take the s off these and make them singular. That's just the general rule. 1 or less, we put a singular referent, and more than 1, we put a plural referent. Okay, now let's consider, now combine the 2 strips end to end as depicted below, so they're attached end to end. If together they are 1 unit long, then how long is the red portion? Express your answer in 2 ways. Okay, so now the 1 unit is all the way across the entire thing. So we're re-unitizing again. This is a 3rd level of unit that we're working with here. Okay, so let's do this by box. Well, how many across this entire thing, right? I have 1, 2, 3, 4. That's going to be 8 there. 9, 10, 11, 12, 13, 14 total across, right? 14 little boxes across, which means that one little box is 1/14 of a unit. So the question is, well, how long is the red portion? Well, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 14ths. 10 14ths of a unit. Express your answer in 2 ways. Okay, so instead of doing 14ths, let's see if we can do 7ths. Each pairing of 2, that's horrible. Let's see how many there are. 1, 2, 3, 4, 5, 6, 7. Right? If you can break something up into 14 pieces, then that means you could have broken it up into 7 equal pieces, because 7 divides into 14. So each of these is 1/7. Each 2 blocks together makes 1/7. So the red is how many of those? Right? Well, there's 1, 2, 3, 4, 5 of those 7ths. So the red could also be written as 5/7 of a unit, if the red and green together make 1 unit. Notice that, again, these are just, once you had 10 14ths as an answer, you could have just divided the top and bottom by 2 and said 5/7 is an acceptable answer as well, because they're equivalent fractions when referring to the same unit. And if together they are 1 unit long, then how long is the green portion? Well, let's use the image that's currently here. The green portion is 2/7 of the entire unit. So 2/7 is one answer. And the other answer is, if I double both of those, it's going to be 4/14. Notice that the red and the green together make the entire thing. And so the answers you're seeing here, the 10 14ths and the 4/14ths, are complementary, meaning that when you put them together, you get the entire unit, right? Because the red plus the green. 10 14ths plus 4/14ths is a total of 14 14ths, and that's 1 unit. Same thing is true if you think of it in terms of 7ths, right? 5/7, its complement with a unit is 2/7, and when you add 5/7 with 2 more 7ths, you complete the entire unit. You get 1 unit. All right, number 9, different strategies for comparing fractions. If 2 fractions have the same referent, then there are various strategies for determining which fractional amount is larger. All fractions below are referring to a liter of milk. Okay, so we're going to just, everything's the same unit, liter of milk. For each pairing, determine which amount of milk is larger and justify your claims using various strategies of reasoning. Okay, so our first pairing, 3/11ths of a liter of milk compared to 5/11ths. Well, because the denominators are the same, we're talking about the same size pieces, Or if I were to take a circle and break it into 11 pieces, which would be hard to do, but imagine I did that, what would be more, 3 of those pieces or 5 of those pieces? Well, clearly 5 of those pieces would be more. In other words, when the denominators are the same, you can compare fractions easily by saying which numerator is larger, because that represents more pieces of the same size. More equal-sized pieces. Right, if each of these boxes represents 3/11ths, we'll say each of those is 1/11th, so there's 3/11ths. Then clearly, if I'm working with the exact same size boxes, right, then 5/11ths would be more. All right, what if we have the same numerator but different denominators? Which fraction here is more? Well, the key to look to, we have the same number of iterations. Each of these is 5 or 8 pieces, but there are 8 copies of what piece? Well, this is 8 copies of 1/15th, and this is 8 copies of 1/17th. So the really question is, which bigger, 1/17th or 1/15th? Well, if you take a hole, let's use a circle for a hole, and you break it into 15 pieces, you're going to have a wedge that will say one of those is 1/15th. And if you were to take the exact same circle and break it up into 17 pieces, so more pieces, which means we should have this is smaller. Right? 1/17th is less of a circle than 1/15th. If you break a circle into 17 pieces, those pieces all have to be smaller, so you can fit 17 of them to reconstitute the whole. So if 1/15th is larger than, let's make this claim. So we have 1/15th is larger than 1/17th, then 8 of these will certainly be larger than 8 of these. That should just make intuitive sense to you, because 8 pieces that are larger than 8 pieces that are smaller. So 8/15ths has to be more than 8/17ths. Now, the confusion happens when students sometimes see the 8 and 8, then they just look to these and say, oh, 17's bigger. And they just automatically think, oh, that means this 8/17ths is bigger, because I see a bigger number over there. But when it's in the position of the denominator, it has the reverse effect, actually, because this means that there's more pieces squeezed into a circle, so each piece is smaller. And then when we do the same number of pieces, right, 8 and 8, then 8 larger pieces is more than 8 smaller pieces. 2/3 and 5/8. Another strategy is to express these in terms of with the same denominator, using this equivalent fractions idea. 3 and 8 are relatively prime. So what we want to do is achieve a common denominator, which is the same thing as finding the least common multiple, which is what we did in our last week's unit. And the least common multiple between 3 and 8, since they are relatively prime, you're just going to have to multiply them. And 3 times 8 is 24. So if I were to multiply this first fraction by, do the top and bottom by 2, sorry, not by 2, by 3, erase that 2, then I can conclude that 5/8 is equivalent to 15/24. If I were to multiply the other fraction, the top and bottom, by 8, to make it the equivalent version of this fraction, and that would be 16/24. Now you are in a position to make a judgment, because you've managed to make the denominators the same. And if the denominators are the same, then we're talking about equally sized pieces, right? 1/24 is equal to itself. And if you have 16 of them, then you're going to have more than just 15 of them. So this favors the 16/24. Another option you could have done here, though, is to get a common numerator, right? So we had 2/3 and we had 5/8. The common numerator would be 10. I can get each of these up to 10 by doubling the 5 and the 8, and by multiplying the 2 and the 3 by 5. And so our fractions are really 10/16ths is another way to write this, and the other one is 10/15ths. But now we're comparing two fractions that have the same numerator but the different denominator. So you really have to think, what's smaller, 1/16 or 1/15? And 1/16 is smaller. So 10 of those will be smaller than 10 1/15. So that again favors the 10 15ths will be more than the 10 16ths. 9 22nds and 15 26ths. Sometimes you can use what are called benchmarks. For example, we know that 11 22nds is the same, if I were to divide top and bottom by 11, is the same as a half. So we know that 9, and therefore we know that 9 22nds is less than a half, because 9 22nds is less than 11 22nds, because they have the same denominator. And we know that 15 26ths, well, a half, I'm using a benchmark of a half. 13 26 would be a half. And 15 26 is more than 13 26, which is a half. So 15 26 is more than a half, and 9 22nds is less than a half. That tells me that 9 22nds has to be less than 15 26. Right? So I compared them both to a half, and they're on opposite sides of a half. That's another strategy, using benchmarks. Here's a benchmark I can use with 1. Right? 19 21st, this is a proper fraction. All proper fractions are less than 1, because this is less than 21 21st, which is 1. All improper fractions are at least 1. Right? 11 over 11 would be 1, but 12 over 11 is certainly more than 11 over 11, and 11 over 11 is 1. So this is more than 1, this is less than 1. In other words, if an improper fraction will always be more than an improper fraction. Sorry, let me say it again. An improper fraction, which is the one on the right, will always be greater than a proper fraction, as long as they're both referring to the same referent whole. In this case, we're talking about liters of milk, right? So 12 11ths liters of milk is more than 1 liter of milk, and 19 21st of a liter of milk is less than 1 liter. So this is using a benchmark of 1, comparing them both to 1. 18 23rds and 17 36ths. Okay, so let's compare 1 23rd and 1 36th. Which of these is more? Well, this involves breaking the circle into 23 pieces. This would be into 36 pieces. Therefore, these pieces would all be smaller. So I know that 1 23rd is more than 1 36th. So these are larger piece than that one. And now notice I have 18 larger pieces compared to 17 smaller pieces. That's a double reason why 18 23rds is going to be more. So 18 23rds is definitely more than only 17 36ths. Sometimes it's said we have more, meaning the 18, larger pieces. Because really this 18 is 18 copies of 1 23rd. And that's more than 17 copies of 1 36th. So you have larger pieces to begin with, and then you have more copies of that, and then you're definitely going to have a larger result. And this last one, 29 30ths versus 26 27ths. Notice that these are super close to being to 1. 29 30ths is just 1 30th away from being 1. So if you were to do a circle of this, now let me actually do a whole circle, a nice looking circle. And there would be a little sliver not shaded. There we go. So what we would have shaded in here, ooh, that's going to be hard to work with. Let me shrink that a little bit. There we go. So what I'm shading is our amount. And what's missing is 1/30. That would complete the entire circle. And what's shaded is 29/30. All right, if I were to do something similar for the other one, so let's just copy and paste this. Let's delete this stuff. And okay, so 26/27. What's missing is 1/27. Right, because you get one more 27th on there, then you have 27/27, so you have the whole circle. What's larger, 1/27 or 1/30? Well, dividing the circle into 27 pieces will produce larger pieces than dividing it into 30 pieces. So 1/27 is larger. So I'm going to make this look a little more obvious by making, even though this is not to scale, it's a larger piece that's missing. So I'm just trying to make this piece that's missing larger looking than that one. And 1/27 is more than 1/30. That's why I drew it larger. Okay, so then what we have is everything here. So what we do have is 26/27. And keep in mind, we're comparing the oranges, the two parts that are in orange. Well, which one would have to be, which one shades more than the other? Well, 29/30 shades more than 26/27. So that tells me 29/30 has to be more, because the part that's missing is, in the 27th case, is there's more missing from the circle in 26/27 than there is missing from the circle in 29/30. Therefore, 29/30 is more than 26/27. All right, so this illustrates a variety of strategies that you could use if you want to determine what fraction might be more or less than another fraction. Okay, now we're going to do a little bit of a reminding of division. Recall the two conceptualizations for division. Partitive or sharing division resolves a missing multiplicand task. It is the interpretation of A divided by B as the operation that answers B copies of what amount make A. Quotitive or measuring division resolves a missing multiplier task. It is the interpretation of A divided by B as the operation that answers how many copies of B make A. Up to this point, we have only performed division that results in a whole quotient, such as 12 divided by 3 equals 4. But in general, a whole dividend and a whole divisor do not guarantee a whole quotient. So even though you divide two whole numbers, the answer you get doesn't guarantee to be whole. Solve each task below, draw a supporting picture, and identify whether you used partitive or quotitive division. Okay, 12 gallons of water fill up 5 equal containers. What is the capacity of each container? Well, the multiplicative structure here would be number of containers times the amount per container, so the water per container, gives you the total water. So the number of containers represents a multiplier. The amount of water per container is the multiplicand, and then the product is the total amount of water. So what's missing in our multiplicative structure? Well, we know 12 gallons of water fill up 5 containers. So I know that we have 5 containers. So let me just put a 5 there. What I don't know is how much water there is per container, but I do know that we get a total of 12 gallons. Let's put 12 GAL. So we're trying to figure out how many gallons there are per container, which means we're missing a multiplicand. This means we're doing partitive division. So our 12 divided by 5 is what we're looking for, and this is a partitive division. Now we're going to draw a supporting picture that's going to help us get to what 12 divided by 5 is. That's the same thing as just doing 1/5 of 12, really. When if you remember, if you divide 12 into 5 equal pieces and keep one of them, then that is 1/5 of 12. But we haven't really talked about how to multiply a fraction with a non-unit yet, so that's coming up. So we're going to approach this as if we don't know that. 12 divided into 5 containers. So I'm going to draw I'm going to do a circle for each circle represents a gallon. And I need 12 of them. So there we go. We've got 12 gallons. And we have 5 containers. So I'm going to do containers as little boxes. Each of these is a container. And we want 5 of them. Okay, so there's my containers and my gallons. Well, there's lots of ways you can do this. You start moving these one at a time into, to do your fair sharing. Figure out how many gallons can go into each one. So there's 5 of the gallons. Right, here's 10 of the gallons are used up now. And I have 2 gallons left. You ask, okay, well, how do I share these? Well, you can share them by breaking them each. I'm going to make them a little bit bigger, just for the representation purposes. And you break this up into 5 pieces. This might be hard to draw. 1, 2, 3, 4, 5. Is that 5? Okay. Pretend those are all equal. It's hard to break up circles into equal pieces. It's easier to do rectangles, but you break each of those up, and then if you wanted to like color code them or something, or you could draw, make a new drawing where you pull them apart. Do something like this. 1, 2, 3, 4, 5. There's your 5 pieces. Rip them apart so that you can then move them. And then it's going to wind up being 2 more can go into each one, because you can do this one at a time. Really is really how I'm doing this. I'm doing 1 piece at a time, or breaking up 1 gallon at a time into each container. And then do the same thing for the second gallon. And knowing that I was going to get 2 of those fifths in each one, I could have just put them in groups of 2 and move them. All right, so this tells me that each container has 2 and 2/5 gallons. Was that gallons of water, right? Per container, which you could also write as 2 and 2/5, right? Each of these whole circles here, that's 5/5. There's 5 more fifths, that's 10/5, plus 2 more fifths, that's 12/5. Or you can write that as 12/5 gallons per container. Notice that our answer, therefore, let's summarize it over here. Or let me go in order. So I'm going to move this stuff up. Just trying to be neat with our notes. We conclude that 12 gallons divided by 5 containers equals 12/5 gallons per container. Well, how convenient is that? The exact same 2 numbers I see here and here made my fraction. Next question is, how many containers are occupied by 12 gallons of water if the capacity of a container is 5 gallons? How many containers are, as soon as we see that how many containers, I know that it's the multiplier that I don't know. It's a question mark number of containers times, and this time I know the capacity of, notice I'm using the word capacity as well. I didn't say how much water is in each container. I'm saying what is its capacity. And the only reason I can ask it that way is because I said that the water, the 12 gallons, fills the 5 containers. So they are reached to capacity. Well, the containers I'm working with in this next scenario are not necessarily the same containers we had before. The containers we had before is they had a capacity of 2 2/5 gallons, or 12/5 gallons. Well, these containers are different capacities. It's the capacity that's changed. So they're not the same containers. These capacities are 5 gallons each. So we know that each, it's 5 gallons per container, and we know that the total is going to be 12 gallons. So you can clearly see this is a missing multiplier. And we're still going to do the operation of 12 divided by 5 to get our answer. Our answer is going to be in terms of containers. And up here our answer was in terms of gallons per container, or water per container. It's probably a better way to say that. Instead of saying water per container, say gallons per container. And this is a quotative. All right, so I'm going to draw the 12 gallons. I'm going to draw the 12 gallons as do a different representation. Up above I did a circle was a gallon. Now I'm going to draw 12 gallons by doing 12 blocks in a rectangle. So there's divide in half and divide in half. So there's 4 boxes, and if I divide each of those into 3, I'll have a total of 12. Okay, so let's specify what's what here. That is 1 gallon. Okay. So we have 12 gallons. And 5 gallons makes a container. So now if I want to do 5 of these together, I see, stopping right here, I have 1 container. We're doing really a unit coordination that's happening here. 5 of 1 unit makes 1 unit of something else. So 5 gallons makes 1 container. 5 more will fill up a second container. But then we need a third container, right, to contain the rest of this. Well, the third container will not be completely full. So unlike the previous example where I said all the containers were filled, this is we're going to have 3 containers, or you might argue that we have a smaller container here, but this is not a good idea to say that there's a large container, and 1 small container, and they're all full. Let's assume that all the containers are of equal capacity, which means that a third container would be needed, right, to pour the remaining gallons into, but it wouldn't be completely full. So the question is, how many containers are filled, or how many containers are occupied? And this can be interpreted multiple ways. You could say 3 containers have water in it, and that would be a true statement. But we want to, on this container that's not full, we want to say what fraction of it is full. So this container over here, oops, that's not the right button. This container over here that's not filled, we want to say what fraction of it is filled and give that as our answer. So really, I want to say that this here represents 2/5 of another container. So my answer to this question is how many containers are filled, if you will. I have 1 container full, a second container full, and then 2/5 of another container full. So the answer is 2 2/5 containers. If you do this in terms of fifths, where each gallon is a fifth of a container, and there's 12 gallons, so we have 12/5 containers, right? Because here's a fifth of a container, here's 5/5 of a container, 5 more fifths of a container makes 10, and then 2 more fifths of a container, and we have 12/5 containers. Okay, and I'm kind of run out of space here because I want to make one last final statement. Let me do this and say that this box is is 1 gallon right there. Okay, and then I'm going to raise all this up to give myself a little bit of space to write the final statement, and that is a division statement. We had 12 gallons to begin with, and we divided that by 5 gallons per container, and quotitive division tells us that we get 12/5 containers needed, or are filled by the 12 gallons. Notice once again, though, when you do 12 divided by 5, and this time with a quotative, the answer is 12/5. Convenient. 12 and 5 surface in my answer like that. This last question here, or this third question I should say, is how many containers are completely full? Now when I phrase it that way, then you're going to say, well, there was 3 containers, but only 2 of them were completely full. So you might make this argument that 2 completely full containers. And another way the question might have been asked is how many containers are needed to hold all the water. In this case, we needed 3 containers needed. These are effectively, the answer is 2 2/5. Well, the answer to the question we asked was, and the answer here is 2 2/5 containers. But the ones that actually got full were just 2 of them. But we did need 3 total just to even be able to put the water somewhere. But the quotitive division doesn't answer one of these 2 questions here. The quotitive division answers how many containers are full and what fraction of the next container is full. So be careful. Some students can fall into the mistake is when they read this question, they're actually interpreting it one of these 2 ways. And so some of them will give you an answer of 2, and their reasoning is valid. And some of them will give you an answer of 3, and their reasoning is valid, even if you were looking for this answer. So you have to just be careful sometimes how these questions are interpreted and how they're answered. In the scenario above, we contemplated containers and amounts of water. It is easy to imagine partial amounts of each of these quantities. Consider the following parallel tasks and ponder the differences. So I kept all the numbers the same, and even the partitive and quotative in the same order. The only thing I've changed is that instead of containers and water, we're talking about cars and children. So if 12 children are split into 5 cars, how many children are in each car? Well, if you put 2 kids, right, each car's got 2 kids in it, and you have 5 cars, you can clearly see that 10 kids fit evenly into 5 cars. And the question is, what do you do with the other 2 kids? You split them up? We don't want to do that, right? We could do that with a gallon of water. We took the 2 extra gallons and split them up, but it's disturbing to think about splitting kids up, and you would not say we have 2 2/5 kids in each car. And so in a case like this, in reality, you would just simply have to say, well, the cars aren't going to have the same number of people, right? 2 cars are going to have 3 people, and the other 3 cars are going to have 2 people. It's the only way to do this because we can't divide a kid into pieces. So we have something that's called a divisibility issue. Number of children is something that's called a discrete quantity, meaning that you have only whole numbers of children make sense. You don't want to talk about 2.5 kids. 2 kids, 3 kids, 4 kids make sense, but so this is a different, this is a trickier question to answer. And you would not simply do 12 divided by 5 and give an answer of 2 2/5, because what does it mean to say 2 2/5 kids? How many cars are, and then here's a quotative version of the same situation. How many cars are occupied by 12 kids if each car can hold 5 children? All right, so now we have, here's a car that can hold 5 kids, so let's put 5 kids in there. 1 kid, 2, 3, 4, 5 kids. make the car a little bit smaller. So there's 5 kids in a car. There's 2 cars now that have 5 kids, but we have 2 extra kids. And we just have a blank space, a blank space, and a blank space in our third car. So, I mean, you could say something like, how many cars are occupied by 12 children if each car can hold 5 kids? You would say 2 cars, and then 2/5 of another car is full. But if I were to say, in the last scenario, how many cars are completely full, you would say 2 cars are full, and the third car is not. But how many cars are needed? You need 3 cars are needed. Does it make sense to talk about 2/5 of a car? And most people don't think of a car as being cut up into pieces physically, but you can certainly say that a car is 2/5 full of kids. So this is just meant to illustrate that when you have things that don't divide nicely in reality, then you have this sort of divisibility issues, divisibility failure, and you have to come up with other ways to answer this. Like in the first case here, you simply say, well, I'm not going to split kids up, so I'm just going to find a way to put 2 kids in 3 of the cars and 3 kids in 2 of the cars, and that will get all the kids in the cars. All right, so some things to think about. And then our very last one, number 11, draw a representation of each scenario below. 7/4 pizzas interpreted as 7 copies of 1/4 of a pizza. Okay, so we have a pizza, and there's 4/4 of it, and then we have a last pizza. So 7/4, well, there's 1, 2, 3, 4/4 right there in this first one. And then I need 3 more fourths for this next piece. And so here's 7/4 of a pizza. And 7 pizzas are equally shared between 4 people. How much does each person get? Okay, all right, so we have 7 pizzas. Let's just do some copy paste. Get rid of that. Okay, there's 7 pizzas, and we're going to share this with 4 people. I'm going to use these little bins to represent a person. All right, so we have 4 people, and we've got 7 pizzas to share. And how much does each person get? Well, one way to do this is to start splitting the pizzas up, putting them one at a time. So that kid gets a pizza, that kid gets a pizza, this kid gets a pizza, this kid gets a pizza. Now we have 3 pizzas left. And these ones I'm going to break up into fourths and split up those fourths. So let's do this pizza first. So there's going to be a quarter. This looks horrible. So let me draw what a quarter would look like. So there's a quarter pizza. Oops. I want to paste that. There we go. And that takes care of that pizza got split up. Now I want to split up this pizza, which means I'm just going to put another quarter in for each kid. And then this final pizza here needs to be split up into quarters and be shared. So we're going to get 1 more quarter per kid. All right, let's just do this. There's split up. All right, so there's the 7 pizzas shared equally between 4 people. How much pizzas each kid get? Well, they get a whole pizza and plus 3 more quarters. But each whole pizza could be thought of as 4 quarters. So if I were to shade how much pizza each kid gets, I was going to shade the pizza for one of the kids, and there's a share right here. We'll call this 1 share. That's how much each kid gets. Well, notice how that compares to just doing 7 1/4. It's the same amount. 7 1/4 and 7 divided by 4 produce the same amount, even though we kind of got there different ways. To do 7 1/4, I started with 1/4 and copied it 7 times. And to do 7 divided by 4, I started with 7 and I started partitioning it into 4 equal pieces. And I wound up getting an answer. Notice that both amounts shaded are equal. 1 whole pizza and 3/4 of a pizza. So this tells us that there's a connection between partitive division and fractional thinking, in the sense that A bths means A copies of 1 over B. So in general, A bths things can be interpreted in 2 ways. You can think of it as, one way is A copies of 1 bth of a thing, which is how I thought of this first scenario, and that's how much pizza it wound up producing. Or when you see a fraction with a numerator of A and a denominator of B, you can interpret that fraction as A divided by B with a partitive interpretation. So in other words, the other way is to think of it as the size of one share when A things are divided into B equal pieces. That's partitive division. And in other words, the fraction A bths represents the same amount as doing A divided by B with partitive interpretation. So there's a connection between division and fractions and how they represent. You can do either way of thinking and arrive at the same final amount of pizza in this case. All right, there's a lot of material there, but that wraps up our first week of a multi-week unit on fractions and their operations. We still have to talk about adding, subtracting fractions, multiplying and dividing them, and a bunch of other things